Welcome class to our first online video for Calculus 1. Today we are doing lesson 11, which is called implicit differentiation. Implicit differentiation is a technique that is used to take the derivative where y is a function of x, but you aren't able to explicitly solve for y. In other words, if you can't get y all by itself, this is a technique that you can use. In this lesson, we're going to learn this technique. We're going to use it to prove the derivative of our log functions. We're also going to use it to prove the derivative of one of our inverse trig functions. We're going to do inverse cosine, and then I'm going to give you the other inverse trig function rules, the derivatives of those functions. You do not need to memorize those. And then as a bonus, I encourage you in Stewart in section 3.6 to go ahead and read the technique called logarithmic differentiation, and that's what those optional deeper understanding problems are all about. Okay, so in this video, we're just going to do the warm-up, and then we'll have a new video for the next example. Before I go ahead and do it, I encourage you to hit pause and try these four problems on their own. Taking the derivative of both sides here, the derivative of both sides here, here, and then observe a pattern in general. Okay, so welcome back. Let's go ahead and take the derivative of each of these functions and see if we can see a pattern. So when I look at this first, we're taking the derivative of both sides. In fact, let's just write to the reader, hey, that's what I'm going to do. So I'm not even taking the derivative yet. The derivative of the left-hand side is equal to the derivative of the right-hand side, right? So that's that derivative operator notation, just telling the reader, hey, this is what I'm going to do. Derivative of stuff in the bracket. Okay? When I look at the left-hand side, what I see is one function of x plus another function of x. So I'm delighted I can compartmentalize my thinking and just think about the derivative of x squared, then think about the derivative of 3x minus 1 all squared. So the derivative of x squared is 2x plus, now taking the derivative of 3x minus 1 all squared. You could multiply this out, but I want us to observe a pattern that uses chain rule. So what I see here is I see a composition of two functions of x. My inside function being 3 times input minus 1. That's what I would do first. And then my outside function is input squared. Input squared. I encourage you to use your scratch for chain rule, but let's just go ahead and do it. Chain rule says the derivative of the outside function, so the outside function is stuff squared. The derivative of stuff squared is 2 times stuff to the power of 1. Evaluate it at my inside function. My inside function is 3x minus 1. And then here's my chain rule times the derivative of the inside function. The derivative of 3x minus 1 is just 3, because that's the slope of the line y equals 3x minus 1. Equals the derivative of 25 is 0. The slope of the horizontal line, y is always 25, is 0. And you can clean it up, but I want to just leave it there so that we can observe a pattern. Okay, in the next problem, we have x squared again, plus a function of x, e to the x, all being squared. So notice that's what we kind of had over here, right? We had a function of x, 3x minus 1, that being my inside function, and now the outside function squaring. Okay? So we're just going to take the derivative of both sides. Derivative of x squared plus e to the x all squared is equal to the derivative of 25. Again, I haven't taken any derivatives yet. I'm just writing to the reader, hey, I'm going to do that. Beautiful. On the left-hand side, I see two functions of x that are put together with addition. So that allows me to compartmentalize my thinking. Taking the derivative of x squared, we get 2x plus the derivative of e to the x all squared. You could use a law of exponents right here and then use chain rule. I'm going to leave it written the way that it is. A function of x, picking up color here, a function of x all squared. Using chain rule, the derivative of stuff squared is 2 stuff to the power of 1 chain rule times the derivative of that stuff, the derivative of the inside function. My inside function here being e to the x. What is the derivative of e to the x? We love this one. It's e to the x. The slope of the tangent line to the curve y equals e to the x is in fact the y coordinate, is in fact the height function, equals the derivative of 25, again is 0. So notice on both of these, when I took the derivative of both sides, they're very, very similar. Oops, sorry, that zoomed out too fast. They're very, very similar. The only difference is that inside function here being 3x minus 1, and here that inside function, let's in fact highlight it. My inside function being 3x minus 1, that's what's all being squared, and here my inside function being e to the x. Let's do another one. The derivative of both sides here. Now remember, when we put a little number right there that's not a minus 1, when it's a minus 1, that's notation for inverse sign. But all other numbers, that is a shorthand for an exponent. This is x squared plus sine x times itself equals 25. I'm going to take the derivative of both sides. Again, the left-hand side is put together with addition, so I get to compartmentalize my thinking. What's the derivative of x squared? 2x plus, what's the derivative of sine of x all squared? Again, we have chain rule. We have a composition of two function of x. The inside function is sine. The outside function is squaring. Beautiful. Chain rule, the derivative of the outside function, the derivative of something squared is 2 times that thing to the power of 1. Evaluated at that inside function, my inside function here being sine x, chain rule times the derivative of my inside function, and the derivative of sine is cosine, equals the derivative of 25 is 0. I dropped my color on this one, might as well put it back in. Okay, so again, I'm differentiating term by term, and on this piece, it's 2 times the inside function, chain rule, times the derivative of the inside function. Let's just see it there. So now, imagine we just have any old function of x, not specifically 3x minus 1, not specifically e to the x, not specifically sine x, but any old function of x. We're going to take the derivative of both sides the exact same way. All right, so I didn't do any math. I just wrote down, hey, I'm going to take the derivative of both sides. The left-hand side is put together with addition, which allows me to compartmentalize my thinking. I'm going to first just take the derivative of x squared, 2x, plus the derivative of a function of x all squared. We saw when we were working with specific functions of x that ended up being 2 times that function of x to the power of 1, chain rule, times the derivative of that function of x. Again and again. All right, so this is no different. This is going to be 2 times that function of x I like using the green. To the power of 1, if you want. Chain rule times the derivative of f of x. Well, the derivative of f of x, we just have a notation for that. That's f prime of x equals the derivative of 25 is 0. You know, an alternative notation, if we had x squared plus y squared is 25, and we're looking at y as a function of x, when I take the derivative of both sides of this equation, you're going to have the derivative of 2x. Sorry, I said the derivative of x squared, which is 2x, plus the derivative of y squared, where y is a function of x. That's going to be 2y to the power of 1, chain rule. This is not any different, it's just a different notation if I want to use y instead of f of x and use y prime instead of f prime of x. Now I don't like writing to the power of 1 because I don't want it to look like a derivative. Equals 0. So the upshot, and we're gonna do this problem again. The upshot here is that when I take the derivative of y stuff, I have to hit it with a y prime. Because y is a function of x, I'm using chain rule. In fact, there's a chain rule every single time. What's the derivative of x with respect to x? 1. The slope of the line y equals x is 1. You could, every single time you take a derivative of x stuff, multiply by 1 right after, and that's using chain rule, but it's overkill. It's been there secretly in the background. Okay. Well, thank you guys for the first warm-up video. I hope that my first video was satisfactory.